All right, so we're continuing our unit on operations of functions and multiplying polynomials. So we are multiplying polynomial functions. When we multiply polynomial functions, we use our exponent rules. So that's how this is going to be. What we did before is going to be useful now. So these are a list of functions that we have here. Now you'll notice we have f of x. This little symbol right here is f. It's pronounced f of x. Right? It's not multiplication, it's the word of. And that just means we have a function in terms of x. Okay? In these particular ones we have excessive variables. It's just for examples, but we name these differently so that I can refer to them later instead of using a y. So here I have f of x, and I say, what's k of x? You can look here and say this is k of x. These y's here are just for examples. Normally if we have k of x, we would only have x in the problem, but just bear with me. Okay? So what we have here, if we look over here, we say what's f of x times t of x. So the little dot means multiply. So that means I'm going to take f of x, this is f of x, and multiply it times t of x. So that's allowing you to see which ones to multiply together without actually giving you the polynomial. So I'm going to do f of x times t of x. So I'm going to rewrite it here so that you can see what I'm actually multiplying together. So this is a monomial times a trinomial or a polynomial. And what we do is we just simply distribute through. It's the easiest route to take. Multiply each one of those, and when we multiply, we use our exponent rules. We multiply our numbers, add the exponents. Multiply the numbers, add the exponents. Multiply the numbers. This one doesn't even have an x, so it stays x squared. This one should be 20. My bad. Okay, and that's it. That's that problem. I would then combine like terms if I could. Remember, like terms have the same variable and the same exponent. So each one of these has an x, but all of the exponents are different, so I cannot combine those. So as I move down, I'm going to lose track of, you're not going to be able to see it on the screen of these. So just keep them. Obviously, you have them on your paper, so it should be pretty easy to figure out. So this is g of x times k of x. So this is g of x, that's k of x, and I'm going to multiply these two together. So I like to just rewrite it with the polynomial here, g of x, k of x, and we're going to multiply these together. There are multiple ways to do this. We've done this before, so if you have a way that's already in your long-term memory, I encourage you to do that. But what you want to do is you want to take each term of these binomials. So each one of these, there's two terms for each of these. Those are binomials. I have to take each term and multiply it times each term of the other one. So 3x times those two, 2y times those two, and that's it. I like to use what's called the tabular method. And when we use the tabular method, like, I don't know, sometimes I just don't like to think too hard. It kind of does, it organizes me so I don't make silly mistakes like I am prone to. I know myself pretty well, and I know I make interesting mistakes. So I create a little grid, okay, like a multiplication grid, and I put each term of each binomial on the side. So this is 3x minus 2y I put here, and 4x minus 5y I put here. You could switch the order, it really doesn't matter. It's just each binomial has to have its own side. All right, so now I simply multiply. It's just like any other multiplication table. So this is 12x squared, this is negative 8xy, this is negative 15xy, and this is positive 10y squared. So now that's the multiplication. Now that I'm done multiplying, I just have to combine like terms. So 12x squared has no like terms. There's no x squared term around here. This one is y squared, so I can't combine those. This one and this one are both xy's, so these are like terms. So when I combine the like terms, I add negative 15 and negative 8. When I combine them, I get negative 23 xy. Now when you combine like terms, you're just adding the coefficient. You're just counting how many you have. And 10y squared doesn't have anything either. So there we are. That's those two things multiplied together. So g of x times h of x is next. So let's try those out. All right, so g of x is 3x minus 2y. Okay, I'm not writing. 3x minus 2y. And h of x is 3x plus 2y. These two are very interesting binomials. They have a special name. Their definition is when you have two binomials that are exactly the same, they differ only by the middle term, by the middle sign, by the sign on the second term. These two are called conjugates. Conjugates. That's gates, like G-A-T-E-S. These have very special properties, and we'll see those as we go throughout this course. Their pattern, they show up a lot, and special things happen, and we'll show you what when we do our multiplication. So it's 3x minus 2y and 3x plus 2y. Now when we multiply together, we get 9x squared, negative 6xy, positive 6xy, and negative 4y squared. So when we combine our like terms, now remember, when you're combining like terms, the signs don't change. So I get 9x squared, negative 6xy, and positive 6xy. That's negative 6 plus 6, which is 0. These, bam, gone, minus 4y squared. So when you multiply these two binomials together, when you multiply conjugates together, you get a binomial as an answer instead of a trinomial or even a 4 terms, a quartic, or a polynomial for an answer. You only get 2 terms. And they are what's called the difference of two perfect squares. So this is 9x squared. This is a perfect square. 9 and 4 are perfect squares. Maybe you realize that x squared and y squared are also perfect squares. And it's the difference of them. And we're going to be dealing with that when we start factoring later. So let's do a little more multiplication. Let's speed it up just a little. So h of x and t of x. So h of x is 3x plus 2y, and x squared minus 5x plus 10. So we're going to multiply these two together. I'm going to give you a minute and have you figure it out and come back and see how we did. All right, so this is how I did it. However you did it or tried it out, as long as you gave it a try, it's definitely a good thing. So notice here, I put the trinomial on the top, and in this case I needed 3. A binomial on the side. You could have done it either way, doesn't make any difference. Excuse me. So when I multiplied it through, I got all these terms, and I arranged them like this, and I could not combine any of them because this one right here should be xy. So this one right here is negative 10xy. So none of them were like terms, so I actually got 6 terms when I multiplied them together. And that's it. That's exciting. All right, this one. Prove. In this class, all the time, we like to prove things. Prove one thing is another, or isn't. Okay? We're asking, is tx squared equal to that? So tx is x squared minus 5x plus 10. They're saying, is this squared equal to this mess right here? Now, normally I'd rewrite it, but it'll take me forever. So I will in a minute. Well, this is not a monomial, okay? It does not follow our exponent rules. This is a trinomial, so that means I need to rewrite it as x squared minus 5x plus 10 times itself. Is that equal to that mess? So I need to do this multiplication and see if those two multiply together is equal to x to the fourth, okay, etc. Okay, so when we set this up, we set it up just like we did any other thing. I'm just moving it over here so I have a little more space. I have a trinomial times a trinomial, and it's x squared minus 5x and 10 on both sides. Since I'm squaring it, each term has to multiply times each term of the other one. So it's x to the fourth, negative 5x cubed, 10x squared, negative 5x cubed. I'm like a Houdini here, but then when I go too fast, I always mess up, so I need to slow down a little. Try it along with me as I do it. And now we just combine like terms. So x to the fourth. Are there any other x to the fourths in this thing? Now here, remember, we're adding. I just did my multiplying, so the exponents changed. Now that I'm adding, I can't change my exponents. So I simply just need to look and combine what's on the outside. So there's no other x to the fourth. I'm just going to minimize this a little so that I can write it over here. Nope. X to the fourth. All right, how about x to the third? Yes, there's two x to the thirds. Negative 5 and negative 5 is negative 10. Remember, when you're adding, if the signs are the same, you know, you have negative $5, you borrow another $5, you have negative 10. Okay, combine these three. These are all x squared, so that's 45x squared. And then we have negative 100 x. This has an x on it. I can't see it, but it's there. And then plus 100. Well, that's the same as this. Awesome. Okay, the problem with proving, the cool proving that we do, is this isn't enough. I can't say, okay, done. They're the same. You actually have to show it. So that means you have to take it. And if you were smart enough to realize this, which I wasn't, you know what I'm saying. I was just worried about doing the math right. So now I have this side that I just did. I have to write that it's equal to this side. So x to the fourth minus 10x cubed plus 45x squared minus 100. Are these the same? Each one of these terms is exact. So x to the fourth, negative 10x to the third, 45x squared, negative 1. Look at that, exactly the same. Now we can say we're done. And that's it. You just have to write a check, and that's good. But one side has to equal the other side, and you have to physically write it. All right, so have a great day.